Hello, math humans. We're going to do 7.6 today. We're going to be talking about linear programming. I think it's a weird title, but that's okay. The objectives are that we're going to solve linear program problems by maximizing or minimizing an objective function using the vertices of the enclosed area. So it's a lot of vocabulary, and so I've kind of defined the vocabulary as we get started. The first thing is optimization. So we're looking for the optimal mix of variables that will maximize profit, because we always want to make the most amount of money possible, or minimize our cost. We want to spend the least amount of money possible. The objective function. So an objective function is going to come from the word problem. These are almost always word problems. And it's going to be an equation that is maximized or minimized. Sorry, crappy handwriting. If we're just doing a problem that doesn't have vocabulary, it often says that the objective function is z. And then if we're doing a word problem, then it would maybe talk about either profit or cost. Okay. Our constraints are going to be the limitations and requirements of the scenario. Two that are often unstated but are always included are x is going to be greater than 0 and y is going to be greater than 0, because these two place our graph in the first quadrant, because it would be weird to talk about making things when you're making a negative product or something like that. So we usually restrict these values to the first quadrant. The process is not difficult, but it is a little bit tedious. From the word problems, we're going to write a system of equations. Those are called the restraints. We are going to graph them, do the appropriate shading. So I would add that word that we're going to do the shading, because that helps to define the area, because we're still talking about inequalities. We're going to find coordinates of the vertices, and I'll show you how to do that in your grapher. Then we're going to evaluate our objective function at each of these vertices, and then we're going to choose the best option, whether I'm maximizing or minimizing. So to do this, I have written out an example, and we're just going to walk through this example together. I might recommend that you pause the video, and I would recommend that you write down the word problem, because there's a lot of words, and so this helps to manage the information. So here is our lovely word problem. We're only going to do one example today because it's a bit long. This says that the liquid portion of a diet is to provide at least 300 calories, 36 units of A, and 90 units of vitamin C. So this is predetermined by information from someone. A cup of dietary drink X provides 60 calories, 12 units of A, 30 units of C. A cup of dietary drink Y provides 60 calories, 6 units of A, 30 units of C. A cup of drink X costs 12 cents, and a cup of drink Y costs 15 cents. How many cups of each drink should be consumed each day to obtain an optimal cost? All right, let's start with the last sentence, because that might help us define our variables, because there's a lot of stuff going on up here. So for my objective function, typically it's going to be something that has to do with cost or profit. And in this one, we're talking about how many cups of each drink, and we know that X sells for 12 cents, Y sells for, that's a 0, 15 cents, and that's going to equal my cost. So this is going to be what we are trying to minimize, because I always want to have, gosh, I can't spell today. I want to have a minimum, that was rough. I want to have a minimum cost. All right, so now I need to write all of my other constraints, and this is actually a cool problem. So I can't show both, so I'm going to write things down, and you're going to have to move your paper so you can see. So the first thing that I'm going to do is I'm going to write drink X. And we knew that for information, it costs 12 cents to make. It has 60 calories. It has 12 units of A and 10 units of C. So that's the information that I know about drink X. I think that the words in the word problem can be overwhelming. so I can start consolidating my information by listing it. Then I'm going to talk about drink Y, and drink Y costs us 15 cents to make, or buy, or whatever, and then it has 60 calories, 6 units of A, and 30 units of C. Now this is actually kind of interesting. We've already dealt with this, so we're not going to use it again because that was part of our objective function. But I need to write a system of equalities. So I did talk about, remember that x is going to be greater than 0 and y is going to be greater than 0 because that gets our graph in the first quadrant. The reason that I've organized my data like this is because I'll use a different colored pen. I think it makes the equations easier to write. So I can only have two variables. So I know that my intake of calories has to be greater than or equal to 300. And I know that I have to have greater than or equal to 36 units of A. And I know that I have to have greater than or equal to 90 units of C. So then when I start writing my equations, this I think makes it look easier. So I'm going to have 60x plus 60y has to be greater than or equal to 300. And then I have 12x plus 6y greater than or equal to 36. And then I have to have 10x plus 30y greater than or equal to 90. So that's going to be, the system of equations that we are going to graph. Okay? So if I simplify, and I'm just going to assume that you can do this because you're brilliant math humans, when I simplify all of these equations, this is going to be y is greater than or equal to a negative x plus 5. And then this equation is going to be y is greater than or equal to a negative 2x plus 6. And the third one is y is greater than or equal to a negative 1/3 x plus 3. All right, so these are the equations that I'm going to graph because my graph is going to look a lot more polite. So what I'm going to do is I'm going to bring in my handy dandy calculator, and I'm going to go to my y equals, and I'm going to clear what's there, and I'm going to enter my equations, but I'm not going to put in the shading because the shading will make it very difficult to manage our graph. And then we had a negative 2x plus 6, and then I had a negative, and I'm going to put it, I'm going to delete that, sad day, and then I'm going to do a negative 1 divided by 3x plus 3, and I'm going to do a zoom 6. There's the first equation, second equation, third equation. So if you'll notice, all of the graphs were greater than or equal to, which means that the shading would go to the right. So I'm just going to sketch this here, but I'm going to pull information. So this is, try to do the colors, this is my red graph, and then I have, let me get a blue one. This is my blue graph, and then this one is my black graph. So I need to find 1, 2, 3, 4 vertices, okay? So on the first one, it's the y-intercept, so I can just do second calculate value, and I'm going to hit x is equal to 0. And it's on the second equation right now. I want it to go up to that one, and notice that this is the point 0, 6. So now I want to find the point of intersection between the red and the blue, as I scribble all over my calculator. So I'm going to do second calculate 5 for intersect, and I'm going to get close, enter, enter, enter. And this point of intersection is 1, 4. Okay. I have the next point of intersection is between blue and black, so second calculate 5 for intersect. And again, I'm just going to get close, enter, enter, enter. And it went to the wrong one, so I'm going to do second calculate 5 for intersect. I'm going to get close on the blue, and then I'm going to make sure that it pops to the black, and I'm going to get close, enter, enter. And it tells me that this one is 3, 2. Sometimes I have to help my grapher a little bit. And then that last one is a 0, so second calculate 0. and it's on the blue line, and I'm going to get, oops, there it is. I'm going to get, oops, I need to be on the black. Whew, sad day. Get close, enter, cross that axis, enter, enter, and I get that this one is at 90. And yes, I could have done it mathematically, and then it would probably been a little bit easier, but sometimes the equations are larger, and it's helpful just to find those points of intersection in your grapher. So now, when I check, remember that my cost function was 0.12x plus 0.15y, and I'm going to write I want to minimize because that was our goal. And so you would need to evaluate the cost function at each of these four indices, or vertices, sorry, bad grammar. So this is 0, 6, and I would run these values through my function. So I would get 0.12 times 0 plus 0.15 times 6, and I get 0.90. And then I would evaluate the cost at the 0.14, and I'm just going to write those values down because you can see how those would be applied. And I get 0.72, and then I would evaluate my cost at 3.2, and I would get 0.66, and then I would evaluate the cost at 9.0, and I would get 1.08. So if the goal was to minimize our cost, the minimum cost happens right here at 0.66. So then I would write my solution as my minimum, that's hard today. The minimum cost is going to be 0.66, and it's going to happen when x is equal to 3 units and y is equal to 2. And then that would be it. So they're really not difficult problems, but occasionally it can be difficult to find those vertices. So that's it for today. I will see you soon.